So this is the AS new spec June 2017 AS2 6B on waves in a pipe. So it says, it sort of has a diagram that looks like this, where we have two pipes closed at one end and there's a loudspeaker at the open end, and it tells you that the frequency is adjusted so that we get the first mode of vibration and the fourth mode of vibration. So obviously if it's talking about sound, we are going to have a node down here at the bottom, and because we're going to hear a loud sound we're going to have an antinode at the top. So again, looking, I've just done out several waves here. When we go from our first node to our first antinode, that is a quarter of a wave, and that is our first mode of vibration. The fourth mode of vibration is going to be when we go from our first node to our fourth antinode. So there's my first antinode, second, third, fourth. Now, so that is 1 3/4 waves, which is 1, 2, 3, 4, 5, 6, 7, which is 7/4 waves. So my L is equal to 7/4. And it wants us to draw in figure 6.1 my first mode of vibration, which I've said is a quarter wave, and then my second mode of vibration, or my fourth mode of vibration in figure 6.2, which is 7/4, so a wave and 3/4. So the easiest thing to do if you're not great with symmetry like myself is to turn it on its side. My node goes here, and my antinode, I'll stretch it out, and then here's the reflected one. Then for this one, I'm gonna just draw my, oh that's awful. Sorry, my diagrams are not great, just fix that. I would obviously have a mark taken off me because that's not great. Try to keep your symmetry. Right. Oh, that's so bad. So where there's an antinode, make sure it matches up with the other antinode. So that is our first and our fourth position of resonance. Now, it tells us that the pipes are 0.68. So I'm sorry, I've skipped on there to part D. Part C is the difference between a node and an antinode. A node is where there's zero displacement, and an antinode is where there's maximum displacement or maximum amplitude. So our length of pipe for each of these is 0.68 meters. Okay, so the same size. And we want to find the frequencies that causes a quarter of a wave and 1 3/4 waves. So I'm going to write down L is equal to, for my first mode of vibration, a quarter of a wave. Again, I'm going to rearrange this in terms of wavelength. Wavelength equals L over a quarter, fraction divided by a fraction. I'm going to flip that upside down and multiply it. 4L, so wavelength equals 0.68 multiplied by 4. So that's going to give me my wavelength to be 2.72 meters. So I'm going to use my V is equal to F wavelength. It tells us the speed of sound is 330. So V divided by 2.72, it's going to equal about 121 hertz. Now, the next part is finding the frequency that this here occurs in. If this gives us a quarter wave, and the next, for the fourth position of resonance, there are 7 quarters in that. So I could just take this and multiply it by 7. And that's going to give me the frequency for that. Which is about 847 hertz, which is my answer. If you need to do it by calculation, just rub this out. So we know that's what it should be. We're going to go back to this, where in this case L is 0.68 meters. We've said that my fourth mode of resonance is going to give me 7/4 lambda. So I'm going to arrange this equation in terms of lambda. Lambda is equal to 4L divided by 7. I'm then going to put in my L of 0.68. So I get 0.389 meters, and then going to put this here for my lambda into my V is equal to F lambda equation, rearranged for F. So it's going to be my V of 330 divided by 0.0389. And when I do that, I get 847.